Hello, my name is Lex Toet, and in this presentation I will give an overview of the current state of the art in visual camouflage assessment techniques. The main approaches to the evaluation of camouflage measures are a subjective approach through observer experiments and an objective computational approach through image analysis. First I will discuss psychophysical evaluation methods, starting with the benefits of field versus lab studies, followed by metrics like detection and recognition range, search and detection performance, visual conspicuity, subjective blending score, ranking and paired comparison, eye tracking measures, mask priming, and more objective methods based on fixation locked event related potentials. Then I will discuss computational evaluation methods like saliency models, clutter and target signature metrics, and search models. Finally, I will briefly discuss new developments and future challenges. I will now discuss some psychophysical camouflage evaluation methods. Camouflage performance in the field is typically considered as the golden standard. However, field trials are costly, time-consuming, and provide little or no control over the conditions, making it hard to repeat trials. Field trials can also be replaced by lab studies, using realistic photo and video simulation techniques. Lab studies are cheaper and easier to organize, allow repetitions both between and within participants, and can be performed simultaneously at multiple locations. However, lab results need to be validated with similar field tests, since human performance in the lab may differ considerably from field performance. This is a typical example of a scene used for camouflage evaluation in the lab. Camouflaged soldiers were registered consecutively at each of the marked locations in the field, and the resulting image set was used in a search and detection experiment. Photo simulation makes it easy to study camouflage performance in different backgrounds. A common measure of camouflage effectiveness is the detection range, that is the range at which 80% of the observers first perceive the target, or alternatively, the distance at which a given observer perceives the target with 80% probability. The shorter the detection range, the more effective the camouflage is. Unlike field trials, which require a physical approach to the target, lab studies make it easy to measure detection and recognition ranges simply by simulating approach sequences, or by varying the simulated viewing distance. Effective camouflage measures should decrease the detection range. In this example, camouflage measure B is more effective, since the observer needs to approach the target closer before it is detected. The outcome of a search experiment is typically modeled by an exponential function describing the probability of detection as a function of time. Effective camouflage measures increase the mean search time and decrease detection probability. In 2001 we published the freely available Search 2 image dataset with many camouflaged military vehicles in a rural setting, together with human lab performance data like search times and saliency measurements. This image set has now been used in over 100 publications on camouflage evaluation and target detection methods. The use of large panoramic scenes enables the investigation of the effects of field of view restrictions and zoom factors on human visual detection performance and search strategies. One can simulate either a large, on the left, or a small, on the right, viewing aperture, with either a large or small zoom factor. Also, using for instance a joystick, one can move the simulated aperture over the entire panoramic scene to study visual search with a limited field of view. The lower image shows an example of a scan path of a small aperture, as indicated by the black square, over a panoramic search scene. Such experiments are time-consuming, requiring many repetitions and observers to get significant results. We therefore developed an alternative approach to quantify camouflage, called visual conspicuity. Visual target conspicuity is operationally defined as the peripheral area around the center of gaze in which a target can be detected in a single glimpse. This area is determined by the contrast between the target and its local background, The contrast both in size, shape, luminance, color, texture, binocular disparity and motion. Conspicuity determines visual search performance, or detection time, since a target will be found quicker when it stands out more from its local background. In contrast to search experiments, conspicuity measurement is easy and fast, requiring only a few, typically 3, observers and only a few, also typically 3, repetitions. For an isolated object like the one shown here, the conspicuity area covers almost the entire visual field. However, when the object is surrounded by similar objects, the conspicuity area shrinks significantly. Notice that it's hard to distinguish the target dot when you fixate somewhere outside the cluster of dots. Size contrast helps to make the target stick out. So does shape contrast, and color contrast, and temporal size variations, or temporal intensity variations, and local motion. Note that camouflage is always relative to a local background. Camouflage that works quite well in a given environment need not work at all in a different one. While camouflage may be near perfect in a given situation, it is broken as soon as the target moves. The conspicuity measurement procedure is as follows. First, the observer foveates the target to make sure that he has full knowledge of its location and appearance. Then he fixates a point in the scene that is both at a large angular distance from the target location and in the frontal parallel plane through the target. This initial fixation point should be sufficiently remote from the target so that it cannot be distinguished at this stage. The observer then successively fixates locations in the scene that are progressively closer to the target position, until he can perceive the target in his peripheral field of view. The angular distance between the fixation location at which the target is first noted is then recorded. This slide shows a schematic representation of the conspicuity distance concept and its associated measurement procedure. Observers start a conspicuity measurement by first fixating at a location x1 in the frontal parallel plane through the target that is far enough removed from the target so that it cannot be detected. Then they move their fixation point towards the target until the target can be distinguished from its local background. Target conspicuity is then defined as the distance x2 in meters in the frontal parallel plane between the target and the fixation location at which the target is first detected peripherally. When all measurements are performed at the same viewing distance d, then the corresponding conspicuity angle alpha c can be used as a relative measure to compare target conspicuity between different camouflage measures. This slide shows how a conspicuity measurement procedure works in a photo simulation study. First, the subject fixates on the left edge of the screen, far from the location at which the target appears, so that it cannot be seen. Then he slowly moves his fixation towards the target. The yellow crosses indicate the successive fixation location. The scan path is indicated by the red arrows. The blue circle represents the target conspicuity area or the visual lobe of the target. In many studies we have shown that conspicuity determines mean search time. Thus, by measuring conspicuity, we can predict mean search time. Also, conspicuity measured on photographs is directly related to conspicuity in the field. Thus, by measuring conspicuity on photographs in the lab, we can predict search time in the field. Conspicuity has successfully been used to calibrate the detectability of targets in daytime and night vision goggle simulations. Making the conspicuity of a target in a simulation equal to its conspicuity in reality guarantees that mean search time obtained in the lab equals mean search time in the field. The subjective blending score for camouflage effectiveness is obtained by letting observers rate how well a camouflage target blends into its background or matches its local background, using Likert or visual analog rating scales. This method is simple and efficient and can be applied both in the field, using scoreboards for instance, and in photosimulation studies. In a ranking experiment, observers order images of competing camouflage designs in a particular scene from best to worst. In the method of paired comparisons, images are presented in pairs, and the observers are required to select which image of each pair contains the most distinct target. Both methods require additional analysis to obtain an overall ranking from multiple observers. Also, both methods yield similar results, but although they yield similar results, paired comparison yields greater precision. NATO RTO SCI 219 on camouflage in hot humid areas used this ranking procedure to evaluate different camouflage designs, both for visual, for near-infrared, night vision goggle imagery, and for thermal imagery. Eye movements reveal information about search processes that cannot be derived from reaction time analysis. Here, the left image shows the search scene with corresponding successive fixation locations, the circles, and scan paths, the yellow lines connecting the fixation locations. The right image shows a heat map representing the duration of fixation on each inspected element of the scene. Over 120 different metrics can be computed from eye tracking data. Some of those metrics, for instance fixation, location and duration, correlate with camouflage pattern conspicuity. Other metrics, like pupil size and scan path similarity, correlate with the distracting effects of visual clutter on human visual search. Increasing clutter leads to longer fixation times and shorter saccades, while fixation duration is longer for targets than for non-targets, and longer than for hits than for misses. Also, pupil size is larger for targets than for non-targets, and larger for misses than for hits. Another camouflage evaluation method is mask priming. This method involves the brief presentation of a target scene, sandwiched between forward and backward masks, and followed by an empty screen with a probe in a position that is either congruent or incongruent with the target position. The masked target is presented so briefly that participants are largely unaware of its presence. Participants are asked to make a speeded response to a dot probe, appearing either on the same, or congruent, or on a different, incongruent, side of the target in the scene. Participants respond faster to a dot probe on the same side relative to one on a different side, while the response speed typically decreases with increasing camouflage effectiveness. Mask priming has successfully been used to quantify the performance of different camouflage patterns, both relative to each other and to the local background. Fixation event-related potentials are an objective way to register target detection, since they eliminate the need for subjective or cognitively biased reports. I will now discuss some computational camouflage evaluation methods. Computational saliency or conspicuity models typically use local intensity, color, orientation, and texture differences to transform an input image into a saliency map in which signal intensity corresponds to an overall local image feature contrast. One of the most popular saliency models is the one by Walter and Koch. However, there are many different algorithms available nowadays. However, they also yield widely different saliency maps. This slide shows a search scene with its associated saliency map as computed with the Walter and Koch model. And this one with Manca's global rarity map, while this one was computed with Achanta's frequency-tuned saliency map. So you see they all differ widely. Saliency models can be used to predict human visual fixation behavior by successively moving the focus of interest between local maxima of the saliency maps. This slide illustrates the simulation of human search and fixation behavior. Note that the algorithm fails to fixate the salient target in the middle of the scene. In general, bottom-up saliency models fail to predict human fixation behavior. Models including top-down processing, that is, object detection through template matching for instance, or segmentation, yield much better predictions than pure bottom-up models. This slide shows an example of a cluttered scene. Clutter is typically defined as the collection of image elements, their heterogeneity, for instance shape, color or size variation, and arrangement, for instance symmetrical, random, locally or globally clustered, that interfere with the detection of the target. Local cluttermatics typically quantify the distinctness of a target by computing the structural dissimilarity between a target and its local background. For static targets, this involves edge detection, texture discrimination, and energy contrast detection. For dynamic targets, this requires correlation, gradient, and energy detection methods. Chameleon is a widely used target distinctness evaluation metric. It computes target distinctness from local energy, spatial frequency, and orientation contrast. Since Chameleon requires the user to manually indicate the target and its local background, its results are highly variable. That is, they highly depend on the actual choice of the selected regions, and they are therefore typically unreliable. Another approach to avoid field experiments is to predict human observer performance using a validated search model. Search models predict the mean time a human observer needs to detect a given target while visually inspecting a scene. These models use either imagery from the scene in question or a list of parameters describing the visual characteristic of the scene, for instance mean luminance of the target, of its local background, and of the overall scene, or the dimensions of both the target sector and the entire search sector, or the dimensions of the instantaneous field of view, etc., to predict cumulative target detection performance. Well-known models are for instance Oracle and VisDet. I will now discuss some new developments and future challenges. Modern warfare increasingly deploys high-tech multispectral sensors and communication systems. Spoofing and adaptive or dynamic multispectral camouflage techniques are therefore becoming increasingly important to enhance the survivability of high-value assets. Adaptive and dynamic camouflage goes back to the end of the Second World War, when the US Navy developed the so-called Yehudi lights, which are lamps placed on the front of an aircraft that automatically adjust their luminance to the average sky brightness. Simulating view from large distance by blurring the images shows the overall contrast reducing effects when the lights are turned on. Together with Germany and Canada, the Netherlands Army has developed a prototype adaptive camouflage system called Chameleon. The idea is to render objects or persons invisible by covering them with a material displaying a camouflage pattern that dynamically adapts its shape, color and brightness to the overall local background. For further details, you can watch this movie about Chameleon on YouTube. British Aerospace Systems developed an adaptive thermal camouflage system for land-based vehicles based on either Peltier elements. In its activative state, it reduces the thermal target signature by adapting to its local background. It can also be used to alter the appearance of the target and mimic other objects, or to display identifiers. The European Defence Agency ACAMS-2 project is currently developing an adaptive multispectral camouflage system for the soldier. The final system will include a combination of several active and passive technologies, providing protection against radar, infrared, and visible sensor threats. The final system will include a combination of several active and passive technologies, providing protection against radar, infrared, and visible sensor threats. The ultimate goal is, of course, the invisible soldier. But even multispectral camouflage will be ineffective against hyperspectral sensors that become increasingly available. Therefore, we need to construct a database of hyperspectral signatures for a wide range of different materials, from which we can derive designated hyperspectral camouflage patterns and display techniques. This concludes my presentation about the current state of the art of camouflage methods and assessment techniques. Thank you for your attention.